Let me extend a warm welcome to all of you this afternoon. We are thrilled to have you with us at what I believe is officially our first CQCS public event. Okay, so thank you all for coming. The center is indeed entitled the Center for Quantum Coherent Science, and we're going to hear a lot of science today. The title of the presentation for today is Living with Entanglement in its many shades. So I'd like to start by just saying a word about what is this center. It's a place where people can gather to talk about the philosophical, the political, the scientific, the technological aspects of quantum mechanics. And in particular, what excites a lot of the core members, the core faculty in the center, are how to take this concept of entanglement and to harness it and to understand it and think about what technologies can come out of it. And that's dubbed by us the second quantum revolution. Others have also dubbed it, but we have put it in print now at least here. So we lay claim to it. Okay. It is an absolute pleasure for me to introduce our panel for this afternoon. We have with us today Catherine Carson. Catherine Carson holds the Thomas M. Seibel Presidential Chair in the History of Science at the University of California, Berkeley. A historian of science and technology, she completed her PhD from Harvard University after working in computational condensed matter physics at Harvard and Chicago. She has worked on the history of quantum mechanics and field theory, quantum field theory, on Heideggerian philosophy, on the history and ethnography of modern research institutions. In addition to several books and edited volumes on these topics, she has chaired the editorial board of the journal Historical Studies in the Natural Sciences. As Associate Dean of Social Sciences, she launched and led Berkeley's new Social Sciences Data Laboratory, D-Lab, co-chaired Berkeley's Data Science Education Rapid Action Team, and chaired the Faculty Advisory Board of the Data Science Planning Initiative. She is a Fellow of the American Physical Society and the American Association for the Advancement of Science. Welcome, Catherine. Sitting next to Catherine is Carl Williams. Carl J. Williams is Deputy Director of the Physical Measurement Laboratory, PML, at the National Institute of Standards and Technology, NIST. He is a Fellow of the Joint Quantum Institute and the Joint Center for Quantum Information in Computer Science, and Adjunct Professor of Physics at the University of Maryland. He directs the Quantum Information Program and helps lead the National Strategic Computing Initiative at NIST. He is a member of the executive leadership team within the PML and represents the PML to other federal agencies. Welcome, Carl. Sitting next to Carl is Leonard Susskind. Leonard Susskind is the Felix Bloch Professor of Theoretical Physics at Stanford University and Director of the Stanford Institute for Theoretical Physics. His research interests include string theory, quantum field theory, quantum statistical mechanics, and quantum cosmology. We will ask you about all of them, Leonard, in this. Professor Susskind has taught at Stanford since 1979. He is widely regarded as one of the fathers of string theory, having with Nambu and Nielsen independently introduced the idea that particles could in fact be states of excitation of a relativistic string. He was the first to introduce the idea of string theory landscape in 2003. Welcome, Leonard. Sitting next to Leonard Susskind is George Lakoff. George Lakoff is the Richard and Rhoda Goldman Distinguished Professor of Cognitive Science and Linguistics Emeritus at the University of California, Berkeley, where he has taught since 1972. He previously taught at Harvard and the University of Michigan. He graduated from MIT in 1962 in mathematics and literature and received his PhD in linguistics from Indiana University in 1966. He is now director of the new Center for the Neural Mind and Society at the Social Sciences Matrix at UC Berkeley. Welcome, George. And finally, I would like to introduce Umesh Vazirani. Umesh Vazirani is the Strauch Distinguished Professor of Electrical Engineering and Computer Science at the University of California, Berkeley. And he is the director of the Berkeley Quantum Information and Computation Center. His research interests lie primarily in quantum computing. He has also done foundational work on the computational foundations of randomness, algorithms, and novel models of computation. His 1993 paper with Bernstein helped launch the field of quantum complexity theory. Welcome, Umesh. So I am Irfan Siddiqui. I am an experimental physicist, and I thought I would give you just a few slides to set the puzzle in place of entanglement before we start our discussion this afternoon. So I take the viewpoint of Niels Bohr, really, in this discussion, so that we can all discuss it afterwards at length for an hour. The format, I should also say at this point, is that we'll have about 45 minutes of discussion amongst the panelists, and we're going to open up to free discussion for another 30 minutes or so with the audience. So get your questions ready as we go through this. You know, Bohr and Einstein went back and forth about this idea of whether, when one makes a measurement, are you imparting a property on the system, right? So there's a famous exchange where Bohr says, in fact, we can't know anything about the particle or the electron until we measure it. And then Einstein says an electron is an electron whether or not you look at it or not, right? And that's sort of what I'm depicting here. We have an oven producing a particle with some properties, for example, spin state, say, right? If we interact this spin with a magnetic field, then there is a definite outcome, spin up or spin down, say. What's very interesting is if I change the orientation of my detector, then in fact the states are right and left, because in fact the orientation of the magnet, certainly according to Bohr, has determined the spin direction. So then what is very, very interesting is if I consider the situation of beyond a single particle, I produce two particles that somehow are intertwined and joined at the hip in the same way. For example, I may produce two billiard balls related to a single cue ball, producing them. Then what happens? Right, here's my oven, which in this case would produce perfectly anti-correlated spins. The quantum statement is that this system cannot be described by its individual parts and needs a holistic description for it. And in essence, they are entangled in every sense of the word. So if I now put two detectors, one for the top and one for the bottom, since they are anti-correlated, I will always measure up then down or down then up. And then the weirdness comes in. What if I measure in the other direction? Indeed, I see also this anti-correlation, left and right, or right and left. And then the weirdness comes in with these three gentlemen, Einstein, Podolsky, and Rosen. What if somehow we were to separate these particles by a distance beyond that which light can traverse? Right? Then could the measurement of one affect the measurement of another? Right? Challenging many notions in physics. And in reality, for many decades, this would remain, if you like, an open question, till this very, very influential man, John Bell, came up with the test to really see, would there be a difference between classical theories or hidden variable, other types of theories in quantum mechanics? And indeed, the test is to break these two particles apart, separate them by a distance that cannot be traversed by photons, and change the angle of the two detectors, right? And indeed, there is a difference between what one would expect between classical statistics and quantum statistics. And the first of these types of Bell test experiments were done right here by Clauser, right, in the 70s, and Friedman. And in reality, they were brought to, I would say, a real turning point in the field by this beautiful experiment of Alan Aspect, right, where using a nonlinear crystal, it weren't spins that were being studied, but rather the polarization state of photons, separated by a distance of 12 meters. And this is the exact plot from his 1982 PRL showing exactly this sinusoidal dependence. Okay. So this is where the story starts. It appears this effect seems to work. It appears that we cannot disapprove this effect. So the question is, well, how has our current understanding changed over these past 80 years of what is entanglement? And moreover, what new technologies could perhaps harness this entanglement? And then, and the final point, should we rethink about quantum mechanics itself? Are there things to add or subtract from this theory? So this is the program for this afternoon. Okay, so I will also join now our panelists. Okay. And first, I'm going to ask Catherine to start off the discussion. Let me see if I can turn this on. It's complicated. Experimental physicist, come on. You can do this. Well, you run the PML, so you must.
I think it's on.
Oh,
it's on.
There you go. It was a test. Catherine, thank you so much for joining us this afternoon. I have this one, I think we're good. So what's tremendously interesting to me is the overlap between the different fields that are involved here in terms of the actual hard sciences, mathematics, philosophy, so on and so forth. So I want to ask you, how did we go from this rosy, smooth classical picture of Newtonian mechanics, right, and Maxwellian electromagnetism, which gave so much hope to physicists at the turn of the century, all of a sudden to grainy, spooky action at a distance? How is it that we went there? And in fact, what were all the classical notions that physicists hold true as truths to be self-evident that we had to lose in this process, or at least challenge in this process?
Well, I'll tell you, he actually set me up. I got to do a slide on this. Do you mind if I show you? Because there are so many good and deep questions entangled in there. I can't make entanglement jokes, right? I wanted to start us off by giving a kind of cartoon version of the history, because we've gotten an introduction to the issues here, but there are so many more that can be unfolded if you walk through the mental evolution that people had to go through as they encountered these phenomena in their lives, in their experience. Think of quantum mechanics, to start, as a really nicely shaped black box with straight edges and sharp corners. That was the intention of the folks who initially thought that they were building it. Let's simply build an extension of classical electromagnetism, classical electrodynamics, and classical mechanics to handle a very small problem around atoms and then molecules. It turned very quickly in the 1920s into the 1930s into a very messy, knotted question, where what started out as was thought to be a pretty straightforward set of problems that could be addressed by small changes to classical equations turned into a set of challenges to our very concepts and ways of thinking about the physical world. Something that started out being about a quantum theory, something just a little different from a classical theory of atoms, molecules, and fields, turned into a whole set of questions around the very foundations of what a quantum mechanics could be. And so from the 1920s, from the invention of quantum mechanics itself in 1925, the creation of a second formalism already in 1926 that predicted the same results but had very different physical intuitions under it, to the debates around uncertainty in 1927, to the opening up of questions around the interpretation of the quantum mechanical wave function and measurements around Bohr and the Copenhagen interpretation, up to the problems that were pointed to around Einstein, Podolsky, and Rosen. The decade from 1925 to 1935 entangled, again, all of very deep conceptual and philosophical questions in the formalism of the theory. The term entanglement, in fact, came out of not the Einstein, Podolsky, and Rosen paper, but a commentary by Erwin Schrödinger writing on it, trying to put terminology, language terminology, around this phenomenon of what he called Verschränkung, or interleaving, intertanglement. It's not a technical terminology that he was drawing on. It was rather straightforward language of things being mixed and tangled up that he introduced into physics. And the foundations of quantum mechanics really exploded intellectually, if not, in fact, historically, from that point forward. So watching as the entanglement, the messiness, goes further, as all sorts of new conceptual questions around the interpretation of the theory of quantum mechanics and of quantum fields unfolded over the course of the 1930s, 40s, 50s, into the 60s, and then realizing that that was not the only terrain on which entanglement would be working. If you imagine, for instance, as it came to be clear that entanglement makes a very real difference in the way you treat real physical systems of atoms, molecules, and fields. This is not simply a foundational problem. It is also a problem that shows up in concrete experimental results and in the descriptions that we develop as scientists to capture them. And out of there spinning off into condensed matter physics. I'm setting up here some of the comments I think that our colleagues will be able to speak to, not as historians, but as actual practitioners. Now, once you get out of the foundations of quantum mechanics into these rather more structured areas, some of the messiness starts to be disciplined, but in different ways in the different fields in which entanglement shows up. This is something of a linear history in the sense of starting from foundations of quantum mechanics and moving into these fields of atomic condensed matter physics. But there's also a break in the temporal narrative when you remember that in some ways at the same time, but in a different set of intellectual conversations, questions around quantum information, quantum computing are being tackled by a different set of people who are structuring the problems in their own way, differently, not the same way as the physicists. And here is where the intersection with computer science that I'm sure will come up among our panel starts to play and introduce all sorts of new notions that have to take a different flavor in physics itself through engaging with the computational approach. And of course, these connect back to each other. This is some of the work done in the 1980s, 90s, and beyond. And yet, there are all sorts of other different, much more speculative, but also farther-reaching questions that come out of entanglement when questions around quantum cosmology, the quantum universe, quantum gravity, quantum, what is the largest possible frame in which this could be put? So rather than directly answering your question, I thought I might, in fact, open up a set of questions for us and for the audience to think through. How do all of these fields actually get messed up with each other? How do we narrate the story of the past that brings us to the present so that we might have some intuitions about the future? Because I think that's the invitation that you've also put in front of us, to ask where this will go, not just where we are, but where it's headed. So that would be my short answer to your comment.
In trying to reduce the echo, I muted my mic, but that means I should know how to unmute it. There we go. Thank you, Catherine. So I want to take the thread where you leave it, in fact, pun intended, of course, with the thread which is connecting all those elements, and say that, in fact, what is our modern understanding now to the panel? Going through these different fields, looking at the intersection with these different fields, what can we say beyond what simply Bohr and Einstein were talking about? And in particular, I want to ask you, Carl, because the atomic physicists, and I pointed to the experiment of Alan Aspect, really were holding down the fort, so to speak, much before circuits were testing quantum experiments or quantum effects. So what did we learn, from 60 years, say, of atomic physics? Right? Have we simply tested the mathematics and said, yes, it works? Or have we learned something more deep about this theory?
So, I think this is an easy question to answer. Atomic physics, the reason that those are the systems, whether it's atoms or photons or small molecules, two atom molecules, we call those diatomics. By the time you get to 5 or 6, those are really complicated. But small systems, atoms, small molecules, photons, they can be easily controlled. And in fact, if you go back and you look about superposition, you ask, what kind of things did we do with superpositions in the 1960s, 70s, and 80s? Well, we built clocks. We built the best clocks in the world. Today, those clocks have a fundamental frequency and accuracy of 1 second in the age of the universe. That's how well we can control them. So we learned that quantum mechanics works. And it works remarkably well. And if you want to go do the Bell's test, and again this last year they've closed all the loopholes that they could think of. Now you have to get more and more speculative about what it is, because we now have the single photon detectors and everything else. So what we've proven is quantum mechanics is a pretty damn good theory. And along came the condensed matter people and decided that they could produce quantum systems that are a little more complex, but could be controlled. And of course, that is where you're at.
So I asked the question because 10 years ago, I gave a talk at NIST in JQI, and you were in the audience. I was talking about these circuits. Look, they look like atoms. And Carl said, but how do you know it's quantum? Is it really quantum? So indeed, there has been a tremendous evolution of extending quantum mechanics beyond the microscopic domain, right? And it's not simply, I would say, even in our condensed matter systems, the ones that are engineered circuits, they simply still have 1 or 2 degrees of freedom. They basically, the Hamiltonian looks like that of a 2-level system or an atom. But what has been tremendous is that we've even gone well beyond that into other fields, including the complexity, really, of the quantum world. So I'd like to ask both Umesh and Lenny to speak to how far can we push this quantum entanglement? What have we learned about complexity in the real world?
Do you want me to give you a physics lecture?
I'm ready for whatever you want, Lenny.
Okay, I'm going to give a physics lecture.
Okay, you want me to cue up the slides?
Yeah.
Okay.
But before that, before we do that, let me say, think of me as a spokesman for almost a generation of young physicists, and some not so young, who are now really involved in a collection of activities which cuts across, in a way that I really find unprecedented, cuts across condensed matter physics, gravitational physics, quantum physics, computer science, in a really, really remarkable way. I have not seen anything like that in a very long career, incidentally. And I find it extremely exciting that these different disciplines are affecting each other, infecting each other in such a dramatic way. Now, where I come from the discipline of high-energy physics, particle physics, but I don't do particle physics anymore. I think much more about gravity. So I'm going to tell you a little bit about how this idea of entanglement has affected some of our concepts about gravity, about space, about time, and especially about black holes. Okay, so I'm going to get behind this thing here just in case you throw rocks or tomatoes at me. Okay, so what makes quantum mechanics different? Well, entanglement and something else, the capacity of complexity, we'll come to that. But I don't have a whole lot of transparencies here, about 50 of them, no more than that. You think I'm kidding, I do, but I'm not going to use them all. All right, so entanglement. You tend to think of entanglement as having to do with entangled particles or something like that. Well, there's a lot of particles in this room, and they are, you're one, and you are entangled. I know. Entanglement can mean many things, but in fact, you're even actually technically entangled. But there's a much larger reservoir of entanglement in this room, much larger than having to do with the particles in the room. It would be here even if the room were completely evacuated and just empty space. It's the entanglement of empty space. What does that mean? How can empty space be entangled? Well, if I were to divide space in half, here you see space has been divided in half by the vertical line there, and I would divide it up into cells. We all know, no, we don't all know, some of us know, that in quantum field theory, the fields in space-time fluctuate. And in fact, those fluctuations can be entangled. If I divide the room in half, I will tell you now that the left half and the right half, their quantum fluctuations are entangled. Here's a picture that shows a region of space divided into 2 parts and divided into cells. Don't worry about the details of the way I divided it into cells, but those cells are entangled. The green arrow there shows how the pattern of entanglement between the left side and the right side of the room take place. Now, don't worry too much about the details. You might ask, what would happen if they weren't entangled? Supposing somebody could make a partition right down the middle of the room and break the entanglement of both sides. something very interesting happens. This we've learned over the last 10 years or so forth. The effect on space of disentangling the parts of it would be to disconnect those regions of space. One way to say that, and the way I like to say it, is entanglement is the glue that holds space together. The entanglement of the different parts of space or the different quantum fluctuations is actually what holds it together. Reinstate the entanglement, allow the two systems to become, the two halves of the world to become entangled, and they become connected again. That is a very dramatic new idea, that space is held together between the entanglements of its parts. Now I want to tell you a little bit about black holes. Okay? Let's take two versions of a black hole game. The black hole game simply consists of Alice and Bob. We all know Alice and Bob. Alice and Bob each have a bunch of particles, a large number of particles. They're very, very far from each other. Those particles have never been in contact with each other, Alice's and Bob's. Alice takes her particles and squeezes them down to form a black hole. Bob takes his particles and squeezes them down to form a black hole. We've created two black holes. Those two black holes are disconnected from each other. They may be miles and miles apart. In fact, let's say they're kiloparsecs apart, very far apart from each other. And I've just drawn black holes as sort of lumps in space. The gray lines inside are the horizons of the black hole. Not very important, the details. Two completely disentangled, I use the word both in a formal sense and an informal sense, two disconnected black holes. Now, this is version 2 of the same experiment. This time, Alice and Bob create, when they're close to each other, that's on the left side over there, way over there, Alice and Bob create a whole bunch of entangled particles. Pairs, what are called bell pairs. They create these entangled particles. The black line between the it's a red line in this picture. The red lines just indicate that those particles are entangled. And then Bob puts his half, his share, in his pocket. Alice puts her share in her pocket, and they walk far away from each other, so they're very, very far away from each other. That's the next picture over there. They're not stretching anything. Those lines are just showing that they're entangled, far away from each other, and then take their particles and collapse them into black holes. The result is two entangled black holes. Because the black holes are entangled, here were the black holes when they weren't entangled. Because the black holes are entangled, the horizons become connected. Just like in that first picture I showed you, when you entangle two regions of space, they become connected. When you entangle the two horizons of the black holes, they become connected. Those two black holes are very far from each other, and yet, by virtue of the entanglement, they're connected through a wormhole. Now, there's a very interesting fact here. It's called ER equals EPR. What is EPR? Well, we already heard what EPR is. It was Einstein, Podolsky, and Rosen, and that was the famous paper of Einstein, Podolsky, and Rosen in 1935, who discovered entanglement. What is ER? ER stands for the same Einstein and the same Rosen, who wrote in the same year a totally different paper about another subject, and the subject was wormholes connecting black holes. What we have found, and when I say we, I'm talking about this generation of young physicists, not me particularly, is that the Einstein-Podolsky-Rosen entanglement between black holes leads to Einstein-Rosen bridges between them. That is a very dramatic fact about space-time and the way space-time is put together. Now, you might say, okay, these black holes are very far from each other. I've got one way off, and Alice has hers on Alpha Centauri. Bob has hers in Brooklyn. Can't they go through the black hole, and can't they go through the wormhole and talk to each other when they get through the wormhole? Well, unfortunately not. Here's what would happen to such a wormhole when it was connected. It would start to grow. Here's a picture of it growing. I love this. I love doing this. Oops. You want to see it again? All right. Here's the wormhole. It starts to grow. Because it grows so fast that nobody can go through it. It becomes what relativists call a non-traversable wormhole. The growth of the wormhole is a phenomenon which saves locality. It becomes impossible to communicate through it. But the growth of that wormhole is also related to another deeply, deeply, deeply quantum mechanical phenomena. It's called the phenomena of complexity, quantum complexity. I won't go into it now, perhaps I'll be asked about it again, but the growth of the wormhole is the growth of the quantum complexity, which is another related concept from quantum mechanics. What I will tell you is we're beginning to see connections between the ideas coming from gravity, the ideas coming from black holes, and the ideas coming from computer science, which appear to be connected in very interesting and exciting ways. And that is my physics lesson for today. Thank you.
Okay, thank you. So before I ask Umesh about complexity, I want to ask you, Lenny, a question on what you said. You know, us lowly experimentalists, we spend years in the lab trying to entangle something, and then it like goes away, poof, in some nanosecond. And you're telling me that everything in the world is entangled all over the place. In fact, I'm missing it. It's right in front of me.
No, the entanglement doesn't disappear.
Mm.
It gets spread into other systems. It gets spread out. You and I are entangled here, okay?
I'm honored. I'm honored.
But then George here bumps into me. All of a sudden, I get a little bit entangled with George. You can only have so much entanglement. You know,
There's a monogamy of entanglement.
Yeah,
I know. I know about this.
Yeah. So you become entangled with some combination of George and me.
Right.
And then you go and you hit Catherine, and you touch Catherine. And Catherine, you become entangled a little bit with Catherine.
Right.
And the entanglement just spreads out so that you're no longer only entangled with me. You and Catherine and so forth and everybody else on your side become entangled with the whole mess here. And you simply lose track of who's entangled with whom. But the entanglement has not been lost. In fact, it's been gained and it's been spread out.
Is it reversible?
Well, that was what Bohr thought. Bohr thought that the development, well, he never really understood entanglement, I think. Maybe he did. But he thought it was absolutely irreversible. And that's why he said when a measurement occurs, the measurement occurs and it's irreversible and the wave function collapses. But in fact, according to the basic laws of physics, nothing is irreversible. Anything that can happen can go the other way. And so this growth of entanglement, which takes place in principle with a sufficiently complex, and I use the word carefully, complex, I mean complex, with a sufficiently complex experiment, we could bring the whole thing back together again so that only you and I were entangled.
Like we were destined to be.
Like we were destined to be.
That's right.
That's undoing an experiment. And Bohr's understanding of quantum mechanics was not able to accommodate that.
All right.
Right.
All right. Pass it to Umesh to tell us more about complexity. Why do we need complexity? We have already quantum mechanics.
Okay, so is it working? Yeah.
Yep.
Let's see. This connection between computer science and physics is a very fundamental one. So if you go back to why computers work in the first place, you could say, well, there's this notion of locality in physics, where you say every particle minds its own business, or maybe just a small neighborhood, and that's something that you can simulate on a computer. In fact, the reason a computer is so powerful is that it can simulate all these kinds of interactions that we see in classical physics. Now, once you go to a quantum system, because of entanglement, you can no longer describe the system by just describing what the individual particles, the states of the individual particles. And in fact, if you have a few hundred particles, the description of the state actually is exponentially large, as Lenny was saying, in the number of particles. What this means is, if you're trying to describe a tiny system of just, say, 1,000 particles, you need more information than you can, well, certainly than you can fit in all your laptops, but more information than you can fit into the entire universe if you think of each particle as containing just a single number. Right? So it's more than the number of particles in the universe. And so then when you think about how complex, how much computational complexity must a system have that's, a quantum system that's evolving in time, what you have to say is that behind the scenes, what must be, here's how we can picture it. Behind the scenes, nature has, for these 1,000 particles, it has 2 to the 1,000 pieces of scratch paper, each with a complex number written on it. And at every moment in time, it's busily sitting around scratching out those numbers and writing new ones in their place. So that's the complexity that underlies quantum mechanics, right? It's the amount of work that's done by a quantum system. And this connection between physics and computer science, which people tried to, there was a lot of interest in it before this connection through quantum mechanics. But what happened is with this connection through quantum mechanics, now this complexity connection has become extremely deep. And now through complexity, you can actually say things about the properties of quantum systems. They are tied up in the complexity of these quantum systems. So the point is that quantum, the way we think about it now, the modern way we think about it is that quantum states themselves have a complexity which is how hard are they to describe? Certain quantum states are very easy to describe, but certain quantum states of just 1,000 particles are extremely hard to describe. The entire universe, classical universe, wouldn't be enough to describe those. And then there's the actual computations or the evolution of the system. And there are certain kinds of evolution of the system which are extremely complex, extremely complicated, and those are exponentially hard to describe. And that's where the complexity comes in.
Great. I'd like to take one of the points that you mentioned. That's for you, George.
Okay.
Okay. Right. You talked about behind the scenes, sort of, and the modern view of entanglement. The history that, Catherine, you were giving us, and sort of the question I was leading us to, is that the introduction was rather in an ad hoc fashion. It was a quantum jump, if you like, right? Where we now have mathematics to describe this. We pretty much agree on the mathematics. We don't really sometimes differ on the interpretation of that mathematics. If we now invert the paradigm and look at the structure of logic, that sort of comes with quantum mechanics. And George, you study systems of logic and their self-consistency and the metaphors that go in there. Is there a self-consistent logic that can explain now, looking backwards, the postulates of quantum mechanics? What does this logic look like? What can we say about the neural mind and quantum mechanics?
Well, first, a little bit about the neural mind. I'll give you the neural mind lecture. Starting with Jerry Feldman's work at ICSI, a program that we worked on together, what we try to do is put together the results from various sciences. So cognitive linguistics, neuroscience, neural computation, embodied cognition experiments, and so on. And after 25 years of doing this, we have some idea of what the neural mind is like. Not a complete idea, but a pretty good idea. And the basic results are these. First of all, every idea you have is a neural circuit. You can't think without that. They're physical. Ideas are physical. Secondly, those ideas come together in forming worldviews. So every worldview that you have has to do with a complex circuit, and you have different worldviews, as you see in this election that's going on. And I've described those worldviews in great detail in a book called Moral Politics and a bunch of articles. And if you care about it, I'll tell you later.
That's more complicated than quantum mechanics, so we can't.
Yeah. Right. But anyway, the idea here is that you can only understand what your neural circuitry allows you to understand. That is, you can only understand what fits your worldviews. And and you're not going to get them. And so if you have different worldviews, you're going to have problems. And you have different worldviews among scientists. There are some scientists and physicists who will say, that it's only through experiment that you can get at reality, and anything that your experiment doesn't show isn't real. That's the Copenhagen interpretation. Then you have another version that says, yes, it is real, and there is one reality, and it goes like this, and you have to have some understanding of that. But both of those use another metaphor, which is that mathematics is in the world. Now, we know from 1963 that this is impossible. Paul Cohen got the Fields Medal in mathematics in '63 for showing that depending upon the set theory that you use, you get different understandings of the continuum hypothesis and its size. So the question is, what is the continuum hypothesis? Well, it can, it was claimed that the continuum was Aleph 1, but it turns out that it can be an infinity number of things if you use forcing, as Paul Cohen showed. They're both forms of mathematics. And if you use something called the Martin maximum axiom, hard to pronounce, you get Aleph 2 to the Aleph 1 as the size of the continuum. And each of these gives you different theorems in arithmetic, algebra, topology, etc., different mathematicses. So there is no one mathematics, and there can't be a mathematics fitting the world where all of them are totally different and fit the world. So we know that. Knowing that, Rafael Nunez and I set out and saying, okay, what do you do instead giving the neural mind? Well, we assume that mathematicians and physicists are human beings, maybe, and the assumption is that they use normal mechanisms, and those normal mechanisms are embodied primitives, frame semantics, and conceptual metaphor theory together with conceptual integration, all of which we could talk about if you want to. But we now have lots and lots of literature on all of this over the last 35 years. And now that's how conceptual systems are structured in those terms. And what we did was show that mathematics and higher mathematics works exactly that way through putting those things together. Now, one of the nice things about quantum mechanics is you get a notion of a wave out of that. So in quantum mechanics, you use a certain mathematics, e to the I theta, or cosine theta plus I sine theta, etc. And those give you the same results. What do they mean? Well, what we show is that each of those things have a meaning. Those things have the same meaning, which is they are functions that are periodic and recurrent, and they change with respect to in proportion to their size, and they're self-regulating. That is, as they get bigger, they decelerate, and as they get smaller, they accelerate, and they form a circle. They form a wave. And that's why these waves are stable if they're standing waves. Okay? So given that, a wave is therefore a function. So a wave in water is a function of time and height of the water. Now, we also know from Fourier series that waves can add up. And we have a mathematics of doing that. And that's a very important thing. Right? Given all that, what happens in quantum mechanics? If you take quantum mechanics more seriously than has been taken by people in quantum mechanics, you can do the following. You can have certain principles that start like this by changing the conceptual system a bit in two ways. One having to do with the quanta and one having to do with wave functions. If you say, look, there are no zeros and infinities in the world. There are just quanta, and there are minimum, and there are maximums like the speed of light, but it's limited, right? Principle number one. Two, when you have formulas such as, energy equals h times frequency, fine. What is that h doing there, and other things having to do with, Planck's constant h? It's not the same number that's involved. It is a proportional constant. It gives you the proportion relating these things. Now, when you have these proportions relating them, there is a Fourier transform that relates them mathematically, which has the structure of a wave function. So if you say, look, each of these is a property, what that says is the properties themselves are waves, that by a Fourier analysis, these properties add up for a particle wave, the whole thing, and that their properties can be mapped from one to the other via a Fourier transform, which is basically has the structure of the wave function mathematically. Okay? So what you're doing is that. Now, things get interesting in two ways. First, if you assume this, there can be no instantaneous event that takes no time. That is a point in time, that is zero. It has to take some quantum. And it has to have, therefore, in it, the pre-state, the state before, and the state after, linked by a wave function that is going to map one wave into another wave within that quantum of time. That wave function entangles those two things. And what does entanglement mean? First of all, not every property is changing. Many properties are the same. If they're the same, then they're the same entities within that period of time. They are identically entangled. The wave function tells you, in terms of your mathematics, you can see exactly what is linked to what part of a wave is linked to another part of a wave. So if you take, for example, you put in to a crystal an ultraviolet photon, and it's going to split into two red ones, and they go off in different directions, they're going to have different wavelengths and different frequencies. And what this does is map the original one, the wave function, is going to connect that to the different frequencies and wavelengths. What that means is they're therefore going to be superposed, and they're going to be connected, and that's what entanglement means. Entanglement means mapping from the wave function. Yep. You also have one more very important part of this, which is the laws of quantum mechanics. So if you have laws for energy and momentum, which link up momentum with wavelength and energy with frequency, what you're going to be doing with those constants, those h's in there, is mapping via a wave function from one to the other, and the mathematics of that will be a Fourier transform that does this. Those wave functions are going to be precisely connecting these things, and that is what entanglement is. Entanglement is not just messy. Entanglement is a precise wave function. Now, the wave function works that way, but one thing we know is that there's not going to be anything that is no zeros. So the result in the world is going to be something that is always going to have some quantum effects, and what that is going to do is give you uncertainty. We can get into that later, but that's the general idea.
Yep, that's a good segue to move on to how to take this particular granularity, all of these features that you've sort of summarized in a nice way, into the technological domain. So in fact, I'd like to call on you, Carl, and also you, Umesh, to tell us, now that we have a good understanding, if you like, from the different viewpoints of entanglement, what technology is on the horizon, right? What can we expect if we are able to harness this? How long is it going to take, and what's dramatic changes are in store for us?
So I think that is probably the most interesting piece. And in some ways, Feynman was probably the first to kind of talk about quantum technologies. I mean, all the way back, some people would say in his 1959 article, Plenty Room at the Bottom, but clearly in his 1980 about how computers, how a quantum computer would work. So quantum computers are coming. And, what are these computers good for? Well, they're not good for word processing. But, again, some parts of the government would like to use them to break codes. But, if you want to do quantum chemistry, that's a good problem. And in fact, there's a whole lot of things in the quantum world, simulating other quantum systems, these quantum computers will be very good for. And I think other kinds of technologies coming out are sensors, amplifiers. As long as you don't care about both phase and amplitude, and you want to only amplify one, we know how to do that trade-off. I can build very low noise amplifiers that are phase sensitive. You may not want somebody shining a laser at the Mona Lisa, but if I'd like to see behind it, I can build and use just a few photons to interrogate. And so we can begin to think about technologies out there that will be the most sensitive instruments we've ever built. And I know I have one of my colleagues who always says, if you need more signal to noise, just turn up the power. Not good if it's the Mona Lisa, or I need a better X-ray, let's just go turn up the power. So building this kind of technology can revolutionize many things that we care about, including our daily lives. And so I think a lot of things are coming down, and the quantum computer is just probably the one that's farthest out.
That was a good answer. I don't know how much I have to add to that. Maybe one thing I'd add to that is that quantum devices can do certain things that you couldn't do classically. So, for example, you can design a pair of devices that can generate true randomness. Okay, but true randomness in a way that you can certify. So you could actually, you could create two devices which you don't even trust, and you take the output from those. And you do a few tests, and based on those tests, you can actually certify that the particular string that that the device's output was truly random. Now, this is something that we had no right to expect, but it's quantum weirdness and entanglement that allows us to do this. So that's maybe an answer.
Just to ask you a follow-up question on that. Yes, sure, please.
Okay.
First. We're entangled, so
Yeah.
your question is my question.
Yeah. I'll be the wet blanket on this. I think what we know, and I think probably Umesh would agree with this, is that quantum computers will not be good for the vast, or will not be exceptionally good for the vast collection of problems that we may ask ordinary computers. We want to solve a problem, typical problem, find your way through a lattice or something like that. You think, well, a quantum computer can try out all possible ways of getting there. No, it doesn't work that way. Mostly we found, I think, that at best quantum computers can speed up a problem a little bit. They can certainly do everything classical computers can do, because you can always run the quantum computer as a classical computer. But they don't do much for the vast class of problems. On the other hand, there are very special purpose problems, and I don't think we know what the full extent of those special purpose problems are. The classic one is factoring large numbers. But there are probably lots of other ones which are very special purpose problems which quantum computers can do exceptionally fast. And I think we don't, I'm not sure what you would say, but I would say we really don't know what the landscape of that collection of problems is and how useful it'll be. We don't know. But I think what you said, I think, which is also certainly correct, is that they almost certainly will be good for simulating science problems that classical computers simply can't simulate because they're not big enough. They simply don't have enough capacity to simulate quantum problems. And so there's certainly a vast possibility of taking physical systems that we don't completely understand, mimicking them with quantum computers or quantum systems, and effectively slowing them down, making them bigger, and being able to manipulate them in ways that you could never manipulate the original systems. That's going to be a big thing, I think.
So let me add one thing to this, because again, it was one of the mathematicians, not a computer scientist this time, but a mathematician, who said, one of the reasons you want the quantum computer is to come up with approximate quantum algorithms. There are many things you do on a classical computer approximately that you can prove actually work quite well. And so having a quantum computer also allows you to find approximate algorithms that may actually be useful, because while they're not exact, they're better than we can do classically.
Actually, I think your point is extremely well taken, Lenny. So, this point that with quantum computers, many of the tasks that we do currently on classical computers would not be sped up at all. Okay, this is something that you have to know about quantum computers. On the other hand, one thing that, one way to look at this issue is, if you go back to there's a story about Thomas J. Watson, the founder of IBM, that he once said in the early days of computers that he could see a market for 5 computers in the world. Okay, so I think the fact is that the way we should think about our tools is that our tools and society co-evolve. So in other words, what quantum computers will be able to do, we know, is simulate quantum systems well. And as we go into nanotechnology, into more and more into harnessing the quantum world, it'll be more and more important to simulate quantum systems. And so you could, of course, we don't know what will, I cannot say what will happen in the future, but I could imagine a scenario where 50 years from now, people looking back would say, I have no idea. Do you realize that once upon a time, 50 years ago, there were people who used to actually find these classical computers useful.
So
I have a question for you.
Quick question, then I have a follow-up too.
It's not obvious from this discussion what it means for there to be a quantum computer. Right? From this discussion, is there a sort of minimal quantum system that you can characterize that would do a quantum what a quantum computation is? Is a quantum computation like just a really fast ordinary computation with ones and zeros, or is it something else that will map the structure of wavelengths, the structure of of waves, of wave functions, and so on? What would it be?
Yeah. So one way to think about this is that your computer is really a physics experiment. It's a very nicely packaged physics experiment. So once you go behind the packaging, it's wires and transistors and voltages and currents, right? And so once you think about it this way, your computer is a way of getting nature. It's a way of tricking nature into solving a problem of interest to you. What you're doing is you're taking a computational problem that you want to solve, and you're posing it as a problem in a form that nature can understand. But then if that's what you're trying to do with a computer, then you have to ask, where is nature working at its hardest? And if you think about the quantum description of nature, well, just to keep a few hundred or 1,000 particles going, nature is putting in more work than the entire classical universe. So why wouldn't we try to build our computers at the quantum level so that we can trick nature into using these exponential resources to solve a problem of...
What does that mean? What would be a minimal case?
Oh, yeah. So now there's one other concept from quantum complexity theory that you have to borrow, which is this notion of universality. That almost anything, almost any kind of interactions turn out to be universal. So just as classical computers, you have to have, as soon as you have basically a transistor, as soon as you have something called a NAND gate, right? You can you can chain those together to build arbitrarily complex circuits. And that's what your computer basically does at some level of abstraction, and the same is true for quantum computers. And in fact, this notion of universality turns out to be just a very fundamental way of looking at quantum systems again.
So I'd like to ask.
Gates physically.
Yeah. So what was the question? Sorry, George.
What are the gates? That
So
is, if you have an AND gate in an ordinary computer and a quantum computer, would you have a corresponding notion of, quote, a gate?
Oh, yes.
Yeah.
Yes, so what you would have is, so NAND gate is already by itself a universal family of gates, classically. Now, quantumly, you have to come up with a set of universal gates. And there are many, so there are several collections of 3 or 4 gates which are universal. So these might involve, some of them are gates that work on a single qubit, and they take the qubit and sort of transform it in some way. And all you need is a few single qubit gates and a single 2-qubit gate in order to get universality.
But you use the word qubit, and and usually that is explained in terms of the Bloch cube, the Bloch sphere, right? So you have something that is normalized to a radius of 1, and it goes around the sphere. Okay, how do you get a gate out of that sphere?
So one of the ways that there's families of logic, for example, that are called C0 gates and other things. So really we need to entangle and control the entanglement between two particles. Right? So basically you have two-partite entanglement in gates. But the question I want to follow up with, and we're ready for our question and answer session, so Erica is ready with the mic, so get ready with your questions. But just to close this thread, Umesh, we talk about complexity, right? And in fact, as you said, nature is doing a lot of work, but there's lots of other complex systems around us that are perhaps at least not obviously quantum mechanical. So there's computing based on neuromorphic architectures. IBM has a true north chip, so on and so forth, to do image processing, vision processing. How would you compare these technologies, right? Are they all different, parts of a different landscape? Are they a mosaic? Are they competitive, with each other? And that's the sort of the last word on this particular topic.
I would say that there are two ways in which quantum computers are completely different from all these other, all these other technologies. The first is they don't exist.
All of them, or some of them?
Yet. Yet. But the second fundamental way in which it's different is there's something in computer science called the extended Church-Turing thesis, which predates quantum, the quantum connection, and it was a very fundamental notion which basically said it really doesn't matter how you implement your computer at an abstract level. The computational power is going to be exactly the same. So all you can change is the speed of your single operation. But for all practical purposes, it doesn't matter how you organize your computers, right? You will still be able to solve exactly the same problems, maybe a little bit faster, maybe a little bit slower. The only model of computation, so the extended Church-Turing thesis is, it's a thesis because it says any reasonable model of computation. Any reasonable meaning you could, in principle, implement it. And so the only reasonable model of computation that we know of that violates this thesis, and in fact it violates it by an exponential factor, is quantum computing.
So this is why we should fund experimentalists to build this thing, because you said it doesn't exist, right?
It not only does it not exist, but if it were to exist, then it's the only one that breaches this, this limit, this fundamental limit.
So it's known to, in fact, be extremely close to the unitary bound.
Yes.
Very good. So I think it's time for questions. So please. Erica, go ahead. What is the fundamental limit?
I'm sorry. So what this thesis says is that basically any model of computation you can dream up is equivalent to the Turing machine. So basically, the Turing machine is just as powerful as any other model of computation you could come up with, except for the fact that once you go to quantum mechanics, that's no longer true. These quantum Turing machines would be exponentially more powerful.
More powerful than the Turing.
That's right.
Yes, sir.
So from my understanding, then, you're building quantum digital computers.
That's right.
Is there any work being done on quantum analog computation?
So again, Disha, so the question is, this analog versus digital question is a very important one. You see, so if you look at the most exquisite experiments that have ever been done, they've been done to something like 16 digits of accuracy, right? So what that means is that if you were trying to build an analog computer, even if you were putting exquisite amounts of effort into getting this kind of accuracy, all you're getting is 16 digits, right? that's not worth the effort. So you may as well build a digital computer, right? And so the point about quantum computers is that at the fundamentals, you have to work through it. It takes a lot of work, but then they are really digital computers, and that's what, so for them to be reasonable, one of the important things was that they had to be digital, they had to be fault tolerant, they had to be tolerant to noise and decoherence. And so there's a huge theory that deals with this, of quantum error correction and fault tolerance.
I just wanted to ask a question about what you just. It seems to me that in quantum mechanics, the division between digital and analog is a very fuzzy one. And the reason is, what I mean by digital is that it's based on zeros and ones. What I mean by analog is that it's based on continuous functions. Yeah. And a quantum state, even if it's just a quantum state of a single qubit, is still described by continuous variables. So it seems to me there's a very fuzzy distinction that's not clear.
You're absolutely right. And in the early days of quantum computing, this was a source of a great deal of research, but also a great deal of anxiety. Because how do you really pin it down? And so it took a lot of fundamental work on quantum error correction and fault tolerance to show that. Okay, so the point is this. So Lenny's point is, you could look at a two-level system, a two-level quantum system. So that's inherently digital because it's zeros and ones. But now there's a continuous element to it, which is your quantum state is described by two complex numbers. Then, the amplitude for 0 and the amplitude for 1, and these are complex numbers, so they're continuous. And so when you have a quantum system, it's this funny combination of digital and analog. But when you actually go to design your quantum computer, you have to make sure that the analog part is really being used digitally. Just like in your digital computer, your zeros and ones are represented by voltages, high or low. But the voltage itself is a continuous variable, but be digitized.
Yeah, it's a tricky business. I'd like to move on to Roger. You have a question, right?
Yeah, just to go back to your original compelling idea about this discussion, which was about correlated particles. And the question is to maybe move to quantum measurements. The question is, are there measurements that you could imagine on physical systems that would somehow be enhanced by looking at these conjugate particle, these correlated systems? One imagines in a sociological context, if you had two people who were diametrically opposed philosophically, you could ask one and figure out what the other person was doing. But are there complex systems, even as complex as the brain, that you might be able to interrogate because of this ability to measure one thing and not the other?
This is a superposition of you two gentlemen, so where should I collapse it?
Didn't understand the question. I think you were asking I'm not sure what you were asking, but it sounded to me like it had something to do with the difference between correlation, simple correlation, and entanglement. Am I misreading the question?
If you have correlated objects,
yes,
correlated particles,
yes,
you make a measurement on one, you learn something about the other.
Right.
Are there ways of exploiting that to make measurements in physical systems that you couldn't otherwise make?
Yes.
Good.
So I'll say something here where people have taken and created entangled images. So you can see one image. You don't have to have both pairs. And you can do things in which you change the phase of one and everything else. You have to be careful here about what you gain because sometimes you're throwing away half your signal, a few other things, but you never cheat the laws of physics. Anybody who comes to you and tells you they know how to cheat the laws of physics, you need to go back and talk with Lanny.
Okay. So what I would like to do. This is great, so we can talk about cheating physics later. What I would like to do is get a lot of the questions, because there's a lot of them out there, so we'll try to have some rapid-fire answers. And in a couple of minutes, I have two special questions for our two panelists on this side. So we're going to get to that in about 5 minutes. So who else has questions? There was a bunch of hands. Okay. We'll get to Seta, then Mark over here.
So, in examples of entanglement, I've often seen spin or polarization. And what measurement could we do to determine if a black hole is entangled?
With what?
With
With,
each other.
with another black hole.
How the
Well-
black holes are entangled with each other? You
Yeah,
said
well,
we
that's
create-
a question. All right, so Alice and Bob have their two very distant black holes, and they suspect they're entangled. They can do operations on them, but they're not allowed to talk to each other for the moment across the big gap between them. Is there anything they can do to confirm that their black holes are entangled? Yeah. They can each jump into their black hole and see if they meet at the center. Yeah, no. I mean that.
Yeah.
I mean that. But of course, there are also other experiments they can do. They can do more or less common garden variety experiments, make a measurement on one black hole, make a measurement on the other black hole, and see if they're correlated. But that's not very interesting.
There's so many black holes. Which one do you measure?
No. Alice and Bob have made their two black holes with their entangled matter, and those are the black holes we're interested in.
Mark?
So you're using quantum mechanics as a tool. But where are we in the understanding of some of the very basic questions like the double slit experiment, why observation and the collapse of the wave function relate to one another?
This is the perfect segue, Mark, to this slide that I wanted to bring up. And we go through this beautiful introduction rather rapidly. Good. So you see, this was put out on the 4th of November. And does anyone recognize the person in the figure? Steven Weinberg, right? Nobel laureate. And it's an interesting title, Why Quantum Mechanics Might Need an Overhaul, right? Still thinking about, in fact, are there really good explanations for a lot of things that we talked about? And in particular, what Weinberg was referring to was exactly this idea of, do we simply calculate, use measurements in the lab to define reality? Or if we have actually some omniscience, some knowledge of reality, does it have to be spread over many worlds? Right? Because, in fact, that seems to be a very popular way of doing this. So I'd like to bring up two questions. First one we'll come around in just a moment, George. But first one I want to ask Catherine, are we ripe for a revolution? Is it time for
The historians always get the hard problems. Historians don't predict the future, but listening to the conversation today, two very interesting things have stood out. We began with quantum theory in the 1920s, and we ended up in two quite different places that the originators of quantum theory would not have expected. One is black holes and all about space and time. The other is about computing. If there is space for a revolution in here, it's from starting from those two places and going backward into quantum mechanics. That is starting from the endpoint, seeing that all of these fields are in fact interconnected, as Lenny was saying when he spoke, and re-understanding quantum mechanics, taking into account the endpoint that we've gotten to now and where we may go. That is, I can't tell you whether a revolution is coming, but I can tell you that if you want to get the signs, it's in looking at the connections between these fields rather than just starting from Bohr and Einstein.
Okay. And so this is tomorrow? That's right. So we'll continue immediately afterwards, George. We'll continue the discussion afterwards as we break up. But I don't want to get before 5:30, Knowles. I had a secret question that I had saved up for you, Carl. And this was the following. You know, in your role, you've looked at quantum technologies across the spectrum in the United States. I'll give you this in the meantime. You know, I get asked the question, you know, where do we stand with respect to the rest of the world? You know, where do we stand in the quantum ecosystem? What is this quantum ecosystem in the United States? What is the role that Berkeley can play? Because you have in front of you an audience right, that's captive and listening and thinking about what is the role of universities, what are the role of the various entities in the ecosystem. So it would be rather amiss if I let this question go. So please.
So briefly on the U.S. versus the rest of the world. This is a field that, to a very great extent, has been born in the U.S., but to a very great extent, it is a worldwide race to see who will dominate it. 10 years ago or 15 years ago, this was a scientific field, and it was a scientific field. I think many of the people who are on the stage look at quantum information science as its own field, and it is a field that has ties to mathematics, to computer science, to physics, and to many other of the domains. So again, this question, the previous question, it really ties right back to that previous question. So if you ask about the ecosystem, well, the ecosystem is one in which academia has a role, but it ain't the departments that have a role. It is creating an ecosystem where the computer scientists, the engineers, the mathematicians, the physicists come together to exploit what is here. It's also one in where we have to start understanding what the technology will be used for. Because unlike 10 years ago when this was just a scientific field, we can begin to see the first niche applications of the field. And those niche applications, remember, the transistor was first used basically as a hearing aid. So you no longer had to have the big bullhorn. I was at the EU rollout of their billion-dollar flagship program back in the spring. And there was a European who mentioned at this meeting, they said, look, the transistor was found not only in the US, but it was also found in Germany by Siemens. They looked at it as just a toy. We will not make that mistake a second time. So the ecosystem has to do with academia. It has to do with getting this information and knowledge out into our high-tech industry so we can exploit it, produce products, tax it, and pay for more science.
All right. This debate doesn't end here. Bohr Einstein certainly could never settle it. So in reality, what I'd like to do here is at least bring this part of the discussion to an end. First, by thanking our panelists. So a round of applause for all our panelists. Thank you for joining us. I'd like to thank the list of people here. Erica Chai is standing there. Sarah is taking pictures. So they're all scattered around here. So thank you to all of these folks here. In particular, to also tell you that the center is evolving. Okay? It's a two-way street. We'd like to hope to have other events, different events, take your feedback, and also work together as a community in our different roles that we have. Right? This is a brand new center. We seek your support in all the ways that phrase implies. So if you'd like to get involved with the center, there's information out there, and in particular, you can put your name on our email list. So that way you'll hear about the events. We have a very large conference coming up to officially kick off the center. I guess this is the unofficial kickoff. But we have an official conference coming up in January. So I'd like to invite you for all of that. And then feel free to have discussions as we go forward. Thank you, and have a very good evening this evening.